I will not be the chair. Andrew will be the chair of this first session, but let me just say that if you need any assistance, any help, ask us or the secretary. They are there to help in whatever you need, okay? So if you have questions also, feel free to ask. For those that are not from São Paulo, I will just say that this city is okay, but sometimes you must be careful with your belongings at the station, and these are people's look. These are the special value here, and so be careful with that. And also, you know, probably if you have walked through the city, you have seen some white stripes painted in the streets. Elsewhere, they are called crosswalks. Here is just decoration. Don't pay attention to that. Don't trust the white stripe as being crosswalks. You might actually be a target, easy target, if you, okay? So I think we can start. So, Andrew.
All right, thank you. So we're going to kick off the school with a first lecture by Dr. Sebastian Dawid, who's going to discuss some details of relativistic scattering theory. So Dr. Dawid is a postdoc at the University of Washington in Seattle. He got his PhD at Indiana University, and he's been working on aspects of few-body reaction theory for quite some time. So you'll give us a nice, thorough discussion and let us know about some interesting aspects for scattering theory and for hadron spectroscopy. So, Sebastian.
Students are supposed to ask questions.
Yeah, please ask questions.
Okay, hello. It's an honor to be here. As they introduced me, my name is Sebastian Dawid. I'm writing my name down, not because you need to remember it, it's not that important. I just need to tell me if this is an acceptable font size for you to see from the back rows. Okay, that's good. If you have questions after the lecture, you can send me an email here. What was the email? And then probably wait 1 month for a reply. Okay, so as Andrew said, I'm going to talk about some relativistic scattering theory. But most importantly, I will talk about this topic in the context of hadronic spectroscopy. It's essentially a field which tries to understand the mass spectrum of strong interactions. Now, the problem with this topic is that it becomes extremely complicated and sort of mathematically sophisticated immediately after you make, let's say, your first 2 or 3 steps. So sort of in order to avoid these complications, I will mostly talk about non-relativistic scattering theory, maybe not even quantum mechanical scattering theory, just classical scattering theory. And then we'll try to build intuition there, which we will use to sort of understand what happens when we study relativistic scattering. Okay, so the overall motivation, as I said, will be to understand the spectrum of strong interactions, or to understand strong interactions in general. Now, I say strong interactions intentionally. I don't say QCD, because QCD is a theory of strong interactions, and strong interactions is something that happens in nature. So it's not necessarily So sure, although we have very good reasons to believe that QCD is correct, that we always have to keep sort of in our mind the possibility that QCD is incorrect for one reason or the other. There's a nice paper by Kenneth Wilson, the inventor of lattice QCD, so this numerical approach to solving QCD, which we'll hear about later today, who said that he invented lattice QCD, this numerical approach to solve this complicated field theory, in order to check whether the theory is correct or not. So in order to make predictions and then falsify whether the predictions are right or not. So even he, this guy who was heavily involved in the theory, warned us, well, we should always keep in mind the possibility that these two things are not the same. But okay, with good approximation, we can assume that they are. So what are strong interactions really? Strong interactions is what we see in experiments. So what are the main experiments that study hadrons nowadays? Anyone can tell me? So by the way, you can ask questions, but I also will ask questions. So it's not one-way road. An idea? Deep analysis, but I'm asking about particular experiments, like facilities somewhere in the world where there are people, they collide things and look what emerges. Okay, yes, Jefferson Lab is one. So there we have, for example, a GlueX experiment, which studies processes like photoproduction of hadrons. You collide proton with some virtual photon and you see what kind of hadrons emerge. Do you know why they study this? Why do they collide these photons with protons, trying to see what emerges? Well, the answer is in the name, glue. Because as we'll soon learn from discussion of this single slide that I prepared for today's lecture, not all hadrons, as Felipe taught you during the online lectures, can be easily classified into this quark, anti-quark, or quark-quark-quark multiplets. So there are states that look like quark, anti-quark, and glue, which we'll call hybrids. And there are certain candidates for these hybrids, like Pi1 1600, so called the spin exotic hadron, that people at Jefferson Lab are interested in studying. Okay, there are other experiments, say BES3 in China. They study their electron-positron annihilation, and essentially what happens is that E plus E minus switch into a photon propagates, then splits into CC bar, quark-anti-quark charm, or charm quark anti-quark, and this CC bar is essentially something like a J psi meson, so which we'll call charmonium, or something else. Many different things can emerge from such a process, and what people want to see there are so-called tetraquarks. And they have candidates like the ZC state. Why do I say candidates? Because, well, this is work in progress. So we are talking about research that's going nowadays, and people don't know the answers. They want to learn what are those states, and they don't know. You can maybe help them. What else do we have there? LHCb, one of the most prolific. So they study essentially proton-proton collisions. They produce a bunch of stuff. Among this stuff, there are B quarks, so almost the heaviest quarks there are. They are, of course, confined in some mesons or baryons, like lambda B, and then they study decays of these mesons, and looking at the mass distribution or energy distribution of the process, they find, for example, states like pentaquarks. And there's a bunch of PC states with different masses that were discovered there. So what I say is that these things and some other experiments like, say, Bell, there's some no longer existing experiments, and so on. This is what strong interactions are. So one could ask a question, okay, we have QCD. Why don't we use QCD to describe these states? We have Quark model. Isn't that all understood? And we're just playing stamp collections, right? We more or less understand the principles that build all these different states. There is no reason to get excited about that. Like, why should I spend my career? If I were you, I would ask myself a question, well, I'm young, beautiful, there's whole life ahead of me. Why should I study this? Why not study dark matter or whatever? Well, and the reason is because we don't really know what's going on. I mean, we understand surprisingly well certain states produced in strong interactions, but there are also some obvious sort of deficiencies in our understanding. So, to give you some flavor of this, I'll try to go through this slide. So, you see all these different labels here in these boxes. Anyone has an idea what's going on here? Like the slightest idea. What's on the y-axis, what's on the x-axis? Okay, it's written, so it's not too difficult. But what we see here is a plot copied from some PDG review, some summary on light mesons. So what they put here, they have some quantum number on the x-axis, they have mass of the meson on the y-axis, and then a bunch of different particles. Okay, so this is the first warning. If you want to study strong interactions, you need to at least prevail over this initial state of fear that you feel when you see all these different particles. Because in reality, there aren't that many of them. You see like 50 states here maybe, or more. But in fact, all those states are just pion, kaon, and eta mesons. Okay, this is a controversial statement, but I'll explain what I mean by that. Essentially, all these states roughly can be understood in terms of QQ bar states, so two so-called constituent quarks. So Gell-Mann-Zweig came up with this classification of mesons. You essentially assume that they come out of, they are bound states of QQ bar states, and just like in non-relativistic quantum mechanics, these can be described by some simple potential, maybe even extremely simple, just like spin-spin coupling. And, well, they are described by their wave functions. Wave function will depend on some radial excitation number, on some orbital angular momentum, some spin of the particle, and spin and orbital angular momentum will combine into total angular momentum of the state. So just like in a hydrogen atom, when you have a proton and electron, you have wave functions. They are also described by these quantum numbers. And you can also, from this simple quantum mechanical model, infer what is the parity and sort of charge conjugation parity of a state. So what's in these boxes is what people try to do here. They took some known states, put them in the boxes, based on these different quantum numbers that are predicted or sort of suggested by the Quark model. So we say we have the pseudo-scalar states, so states with total angular momentum J and negative parity, and according to Quark model, based on isospin considerations that you heard about from Felipe during online lectures, we can put this SU3 9 states, which compose our one isovector, which is pion, two isoduplets, which is K plus, K minus, and K naught, K bar naught, and two isosinglets like eta, eta prime. We can assign orbital excitation L to them. We can assign radial quantum number 1. So this is the lowest excitation, and they have the lowest mass. Wonderful. So what are those states above? Pi, K, eta, eta. Well, they have the same labels, but different masses. Well, you can say those are the same QQ bar states, just a higher radial excitation, number 2. And then there's number 3. So you don't have to think about pi 1300 as a different pion than this pion. It's essentially the same state. It's just a higher wave function. Like you don't think about excited hydrogen atom as a different particle than regular proton-electron state. Okay, so all these pions are really the same, sort of the same state in a sense. They come from the same microscopic description. Okay, Rho is also like a pion. It has just higher angular momentum. So it has angular momentum excitation. And so is K star and omega and phi. And then we can also radially excite Rho to 2 and 3. There's nothing here. If you go to orbital angular momentum L1, then instead of 2 boxes, we have 4 boxes. Why? Because we can have spins that are aligned or anti-aligned. And then if we consider orbital angular momentum configurations that give you given total angular momentum, there are 4 of those. So you have 4 boxes. We have particles that are called A. A means essentially like a pion, but instead of minus plus, you have plus plus. A0 or A naught means that total angular momentum is 0. So A2 will mean that total angular momentum is 2. But it's, again, essentially the same state, is just a different excitation. If we look, for example, at states with plus minus, they change the name to B. Instead of etas, we also use Fs and H's. But these are all essentially the same states if you look at them from this microscopic point of view of quark anti-quark model. Okay, but this picture, although it's insanely successful, right? We have all these different, what you'd call particles, and I just told you that they are really the same object, just QQ bar state, different excitations, just like in a hydrogen atom. It's insane that such a simple model could work, right? This model, in reality, doesn't really work that well. So what I told you is a fairy tale. And we've been learning or starting seeing cracks in this fairy tale in the past 20 years. Essentially because people started discovering more and more so-called exotic hadrons, so states that are not easily, by definition, not easily described by this fairy tale. And I have some arrows pointing to this numbers here. Essentially, this numbers means sort of asterisks mean in this review are described as some, well, controversial states or controversial assignments or uncertain assignments. Because, for example, this pi 1800 is difficult to understand it, like the mass hierarchy in a given multiplet. If you assume it's just a QQ bar state, some people suggest it might have this gluonic component, like this pi 1600 state. there's a bunch of these F-naught states that some people claim they are strong candidates for glueballs. So states that have no quarks in them, or so-called constituent quarks, are just made of gluon and gluon bound states. So these appear as scalars. It also can appear as a tensor. There are some states where we're not really sure if this one should be put here or another one that's also discovered and has a nearby mass. There are states that are possibly tetraquarks, as some people claim, so not just QQ bar states. And then there is also, you can compose the lighter nonet of scalars from known particles that have very interesting properties. Some people claim these are tetraquarks. Some people claim these are just weird pi-pi or KK resonances. So you see that it's not that simple. So imagine a situation in quantum mechanics where the lecturer starts telling you about Schrödinger equation for the hydrogen atom and tells you, well, we understand hydrogen atom up to excitation n equals to 2. 3, not so much. And also, if we start adding spin and orbital angular momentum, which is not usually done when hydrogen atom is introduced in quantum mechanics class, then also there are some weird things that start happening and we don't understand them. So imagine someone told you about this, claiming that quantum mechanics is a great success, but we haven't really understood hydrogen atom after 100 years. So you'd say, well, maybe we didn't understand hydrogen atom that well. So here the situation is very similar. We have a very good crude model of what's going on that sort of explains these different patterns between states. But there's a lot of things that do not really seem to work. Okay, so what are the ideas? How to explain, how to... Sure? Yes, so there are no widths. Wonderful question. I was supposed to mention that. So this fairy tale is even more dubious to some extent, because I told you that mesons are bound states of quarks and antiquarks. But in reality, they are not bound states. What is a bound state? Bound state is a state that doesn't decay. It lives for infinitely long. All the states decay through different processes, including electroweak processes, but if you turn off electromagnetic and electroweak interactions, most of the states decay through strong interactions as well. So they have widths. They have non-zero widths. I'll talk about widths probably later during the lectures, but you can think about this. They have non-zero lifetime. After something like 10 to minus 23 seconds, 10 to minus 24 seconds, they will decay. So in reality, all those states are unstable, and calling them bound states already is a great simplification. I mean, so when you talk about shape, you mean, well, we do perform some scattering experiment. We look at the mass distribution or energy distribution of the final states, and we see some bumps there. And if a state is, let's say, as isolated resonance, whatever that means, I'll explain that later, you will see a clear single bump, let's say, and you can interpret the width as the lifetime or in terms of lifetime of a particle. Now, the glue balls, as far as I remember, I'm not an expert on this particular topic, but glue balls appear through these F0 states that appear in some very complicated patterns in, let's say, like pi-pi reactions. There is no clear understanding whether these states are globals or not, because in the final states they can mix with quark-anti-quark states of the same quantum numbers. So in other words, these globals that appear in real life are not really like eigenstates of QCD that we would call globals. They mix with some other states, and they are essentially superpositions of some QQ-barren global states. So it's a great problem how to say what is a global or not. I don't think it is possible to tell that from the width that you observe. I think you need to study other processes in order to distinguish a global from a QQ-bar state. Okay, how am I doing on time? Oh my goodness, and I'm on first half page of 10 pages for today. Okay, so back to my point. Hydrogen atom. This is like hydrogen atom for QCD. If we want to say we understand that, we need to understand all the radial excitations, orbital angular momentum excitation, and so on. So what are the tools that are on the market? Some of them we'll hear about later. Lattice QCD. We say, oh, forget about quark model. QCD is the real theory, quantum field theory. It all sounds so fancy, it's complicated. There's Lagrangian fields, etc., colors, symmetry groups, and so on. It's non-abelian, whatever. Let's put it on a computer, solve it non-perturbatively. We know that QCD is hard because it doesn't allow you to describe low energy physics, which sort of all the states belong to, using perturbative expansion. So the simple things you learn, like Feynman diagrams in your quantum field theory classes or perturbation theory in quantum mechanics classes. But you can solve it on the computer and essentially get the spectrum. Well, there are other ideas. There are so-called Dyson-Schwinger equations. I'll just write them down so you sort of hear these names at least once in your life. There are EFTs, something we'll hear about from Andre, like current perturbation theory. There are pionless EFTs, so EFTs of baryons without light mesons, etc., that we can also use to sort of understand these different states that appear. There are quark models, or in general models, that try to mimic QCD in some way. You can use simple quark models with some non-relativistic potentials. You can do, you can add some relativity to them. You can build your models on some light front arguments, some ADS, CFT correspondence, and complicated things like that. Or you can study sort of semi-classical approximations of QFT. So try to understand particles that appear in the spectrum of strong interactions as, let's say, solitons or instantons, or some other sort of non-perturbative solution of classical equations of motion. So now, one underlying characteristic of all these approaches is they're too difficult for me to understand them. And it's a lot of math, and I'm very poor at math. This is my personal bias. There's one more characteristic, which is they all make some assumptions about some microscopic mechanism that leads to emergence of these states. So we have some fields that interact, some gluons are exchanged, or we have some quarks, heavy static quarks interacting via some potential, and so on. there's always some microscopic mechanism that is assumed because we have this sort of philosophical tendency to try to explain certain things in terms of smaller, simpler things. But of course, we don't need to do it this way, and this is what this lectures will be about, if I don't run out of time. Because what I want to talk about is something that does not rely on any microscopic description, and comes under the name of S-matrix theory. So S-matrix theory is something that has been studied in the context of hadrons a long time ago before QCD was created, because people saw all this mess and they believed there's no way to build field theoretic description of hadrons. Well, those people were proven wrong, but they made a lot of progress in studying properties of scattering outside of any microscopic assumptions, or almost making as few microscopic assumptions as possible. So this gives you a very general tool to study states that appear in all these scattering experiments based on very fundamental principles of physics. So as I said, this idea of building theory of hadrons without making any microscopic assumptions eventually failed. We came up with better schemes of computing properties of hadrons. But nevertheless, it's not completely useless, because you can use the results of S-matrix theory to build some model-independent parameterizations of scattering amplitudes that then can be used either to study experimental reactions or study numerical experiments that we perform in lattice QCD, or even study some non-perturbative aspects of EFTs. So the power of S-matrix theory comes from the fact that it's so general, it can be applied all to these different theories or models. Okay, so if we want to talk about S-matrix theory, we need to say what the S-matrix is. So I think this was done during the online lectures, just to remind you. It will be very simple. Again, I don't know complicated math. So we have some states that enter, mess happens, and then some states come out. That's about how sophisticated I will be during this lecture. So what we say is, if we describe this state by some ket alpha and outgoing states by some bra beta, we'll have some operator, linear operator, that takes this and calculates lets us calculate the overlap with the outgoing state, and this is the S matrix. Or actually, this is the S operator. The S matrix would be the matrix element of this operator. There's a lot of theory that goes into the definition of the asymptotic states. You could, of course, connect your S operator to some microscopic description. You can say that this S operator is a product of two molar operators, where molar operator is defined as a product of evolution operator for free theory times evolution operator for interacting theory, taken in the limit time of interaction going to plus or minus infinity. You can write this operator as a time-ordered exponential of your interaction Hamiltonian and so on. This is all complicated. We just want to think about scattering in very simple terms. Something happens. We don't care about what happens in the middle. It's described by that. Something comes out. Forget about complicated math. Okay? And of course, the probability of reaction is proportional to the square, modulus square of this matrix element. Okay, so the S-matrix theory, the goal of S-matrix theory is to answer the question, how much can we tell about this object without knowing too much? And this is what the lecture is about. Okay, let me start. Before I talk about these principles or how to answer this question, let me give you a short overview of the history of S-matrix theory. So the S-matrix was introduced, maybe that should be turned into a question. Who introduced the S-matrix? Such a basic concept, you've probably learned about it in quantum mechanics or quantum field theory, but who introduced it? I have a more difficult question for you. If you don't want to learn S-matrix theory, but you want to learn quantum field theory, who introduced the concept of field in physics? Okay, you know, you're one of a few people that knows the answer. It's a very interesting story, but we don't have time for that. So the person who introduced the S-matrix was Wheeler in 1937. So there are three fathers of S-matrix theory. Wheeler, then there was Heisenberg, who understood, I think in 1943, that you can study properties of S-matrix outside of any Hamiltonian or microscopic concept. And then there is Berg, 1944, who made probably the most important contribution to the S-matrix theory. Andrew, do you know? So all these three people were absolute geniuses, but one of them wasn't a physicist. And I'll let you guess which one wasn't a physicist. Okay, see, that's a real puzzle, this one. So what did Berg do? Who was Berg? Berg was a genius. He was a graduate of Princeton University, but I think in linguistics, he knew like a bunch of languages, Latin, Greek, Sanskrit, etc. But his career was in baseball. He was a baseball player. So Berg was a brilliant guy. He was people were surprised that he was playing baseball because he has such intellect. During the war, he decided to enlist in the US Army, and people recognized that he was very smart, he knew a lot of languages, so of course he became a spy. He became a spy with a very specific mission of infiltrating the circle of European nuclear physicists. For two reasons. First, the US wanted to hire as many smart European physicists to work for them. And secondly, Americans were aware that Nazis were also working on their own nuclear bomb project, who was, by the way, led by Heisenberg. So Berg had this mission. He stayed for, I think, many months in Europe, talking to mostly Italian nuclear physicists. But then came an opportunity, rare opportunity, that there was some conference. This was during the war in 1944. There was some conference where Heisenberg was supposed to appear. This was very rare because if you wanted to go to the conference and you were sort of the leader of the Nazi nuclear bomb program, you'd have to get special permission, etc. But Heisenberg got this permission, went to Zurich, and Berg got a mission. You go to Heisenberg's lecture, and listen what Heisenberg has to say about their advancement in building nuclear bombs, or their understanding of nuclear reactions in general. And if from the lecture you figure out that Nazis understand nuclear reactions as well as we do, you have to assassinate Heisenberg. This anecdote is not completely fabricated. It really happened. Berg went to this conference with a pistol in his pocket, with a cyanide pill in another pocket, with a mission to kill Heisenberg if they know too much. So he went to Heisenberg's lecture, spent an hour there, listening about S-matrix theory. And after the lecture, he said, this was so boring, there's no way Nazis know how to build a nuclear bomb. And he didn't kill Heisenberg. That's why he should be considered one of the founders of S-matrix theory, because he realized that it was boring. But hopefully these lectures won't be as boring. Okay, so people were built, these were the founders. Then the program of understanding what this S object is without knowing anything about microscopic sort of description of reality was sort of picked by Mandelstam and True, and then many others like Olive, Gell-Mann, Goldberger, and many, many other people who did a lot of work on trying to understand how to answer this question. Like in parallel, around 50s, so this was a program that was going on from 50s, maybe even to 70s, I would say, late 70s. In parallel, there were people who tried to understand the S matrix from the point of view of generic quantum field theories. So those are people that now we call axiomatic quantum field theorists, like Weitman, say Hack, well, and some other people that I have written down, but it's, and of course LSZ people, so Lehmann, Semantic, Zimmermann. And they made a lot of progress by understanding the following idea. Although in experiments, when we scatter two hadrons, the energies and angles at which these hadrons scatter or emerge are real. If we complexify these variables and consider S matrix as a complex function, and then impose some fundamental properties of physics that we believe must be true on this complex function, expressed as some constraints on the analytic structure of these functions, you can learn surprisingly a lot about what scattering should look like. So we need to make this step. Instead of thinking about scattering as a process that occurs with real energies and real angles, we need to consider complex angles and complex energies and maybe other things that are complex and sound even more insane that we'll, I hope, talk about tomorrow. So their idea was that fundamental principles must be right. S matrix is a simple object that describes what happens without going into details about what happens in the middle. The space of fields in quantum field theory is much, much larger than, makes many more assumptions than these fundamental properties of physics. And just to give you an example, let's consider a Lagrangian. It's probably first and last time when we write a Lagrangian during these lectures. The following scalar field theory. Okay, it has kinetic term. There will be no mass. This is a massless field. And then we'll add some interactions. Simple Lagrangian. What it describes, we have a kinetic term with a 3 or 5 to the third interaction, but with some momentum dependence that comes from these derivatives. And you have quartic interaction, again, with some momentum dependence that comes from this derivative. So now I have a homework problem for you. Maybe some of you can solve it immediately with your expertise of Feynman diagrams and so on. Compute a 3-level amplitude for this simple reaction. So essentially something like diagrams like this. So when you get the answer, come to me, and I'll tell you that you could have guessed the answer by knowing the fundamental principles of physics without doing any calculation. For some particular reason. Because this Lagrangian, to some degree, is very special, if you look at it, stare at it long enough. Okay, so, as I'm running out of time, let me skip this and talk about these general principles. Okay, you want to be physicists, I hope. It's a tough career. Have to give lectures in the morning. What are some fundamental principles of physics that you think are important if you want to study scattering? Or maybe let me phrase it differently. If you see some theory of scattering, someone gives you on a paper some theory of scattering, whatever, and you see, oh, this principle is broken, this must be wrong. What kind of principle would that be? Okay, very good. So you have conservation laws. Now, conservation laws like energy or momentum or angular momentum they come from symmetries. Like, for example, Lorentz symmetry. Or actually Poincaré symmetry. Things like charge conservation will come from something like U1, global symmetry, etc. of your theory. Isospin conservation that Felipe talked about comes from SU2, global symmetry. Very good. If your theory breaks energy conservation, it's at least very suspicious. Other principles. Yes, sum of probabilities should be 1. So we will call it probability conservation. Probability conservation can be also expressed as unitarity of the S matrix, or this S operator. Conservation laws, so this will be a strong constraint on what this S operator can be, or S matrix can be, and we'll talk about this during third lecture. The third lecture will be devoted to the single equation. Conservation laws will turn out to reduce the number of matrix elements necessary to describe a reaction. For example, if we have some amplitude that depends on 25 different momenta because there are 25 incoming or outgoing particles, if we impose momentum conservation, well, we know that incoming momentum has to be equal to outgoing momentum. We could get rid of 3 degrees of freedom because there are 3 conserved momenta x, y, z. Okay, other principles. This is getting more difficult, I have to admit. It's something that's not necessarily given by probability conservation, but is sort of implied by this equation, which is that S matrix is a linear operator. That it takes incoming states, performs linear operation on them, and gives you outgoing state. That's a sort of often forgotten assumption, because in principle, why should physics be linear? But if we say that S matrix is unitary, that means by definition it must be linear and satisfy this equation. Okay, how about things like cluster decomposition? Is it something that rings a bell or you would consider a fundamental property of physics? What is cluster decomposition? Cluster decomposition says that if we have 2 events that happen far away from each other, they shouldn't affect each other. It's essentially, one could say it's a consequence of Lorentz symmetry. But well, I don't think axiomatically, in terms of Weidmann axioms, it is necessarily. So you can consider it as another principle. Causality. Again, one could say this is something that is part of Lorentz symmetry. But again, it's so important that we should consider it as an independent property. So cluster decomposition will essentially mean that if we have S matrix that describes 2 events that are disconnected from each other, we will be able to sort of factorize S matrix into products of 2 S matrices that describe independently these 2 processes. Causality, and this is the microscopic assumption that we will make, locality. So the fact that interactions that we want to study are finite range. And there are different types of locality. Ultra locality, which means that they have finite range in a sense that they are exactly 0 outside of some radius. There is more refined locality, which is that they decay exponentially, like Yukawa potential. They will tell us that these objects, matrix elements of SB, must be analytic functions of scattering parameters up to some singularities that are allowed by other principles. But if you know the theory of complex functions, you know that holomorphic functions or analytic functions are very heavily constrained because they satisfy Cauchy-Riemann equations, and its sort of class of holomorphic functions is very, how do you say it? Stiff is not the right word. It's highly constrained functions. Okay, anything else on my list? The least obvious, crossing symmetry. I don't have space here. A crossing symmetry is essentially a statement that if you have some process described by, let's say, two particles going into two other particles, you can switch a particle in the incoming state with an antiparticle in the outgoing state. And the matrix element of your S matrix that describes these two states are identical. It's essentially a consequence in the language of axiomatic quantum field theory. It's a consequence of CPT, symmetry, and Lorentz invariance. So CPT meaning parity, time reversal, and charge conjugation reversal, so switching particles with antiparticles. If you also impose that your scattering amplitudes have to satisfy Lorentz symmetry, or Green's functions have to satisfy Lorentz symmetry, and you perform some wild analytic continuations of your Lorentz symmetries, taking complex Lorentz boosts, you can connect different kinematic regions that describe different processes that I just said with particles exchanged, and show that they are the same. There are two ways in which crossing symmetry is typically understood in literature, either some permutation symmetry between kinematical parameters that describe a process, or exactly in the sense that I just said, that functions describing this different processes are just analytic continuations of the same underlying function. So imagine that everything that I just said is in this box. Internal set, okay, and two more principles. I have 2 minutes, so that's great. That we will assume, I mean, they are maybe not that fundamental, but they will be fundamental for the description of scattering that we want to sort of study in the next 2 lectures. Existence of mass gap. So this is an assumption that will be necessary for many theorems that we will discuss to be true. Mass gap means that there is some lowest non-zero energy scale in the scattering problem, like, for example, a mass of an exchange particle. So an example of theory that doesn't have a mass gap is QED, quantum electrodynamics, because there are photons. They give you the lowest energy scale, which is their mass, which is 0. And then many theorems that we'll discuss will not hold for QED. Although it doesn't mean that you cannot define scattering for massless particles. And then the other important assumption that we will have to make, which doesn't immediately feel fundamental, is pole-particle correspondence. We'll say, and it's sort of a philosophical to some extent, we'll say that if we see a pole in our S-matrix element that's a complex function, so it can has pole singularities, it will correspond to a particle. Although at some levels this correspondence is not necessarily obvious or maybe even true. Another thing that's important that's sort of given in field theory by LSZ reduction, and we will have to assume in our S-matrix theory that doesn't want to use LSZ reduction, is that S-matrix elements at particle poles will factorize. So if we have something like a generalized Mandelstam variable, Maybe I should put 3 dots here, okay. And the scattering amplitude goes to, blows up because it has something like term like this in it. Then just like in the cluster decomposition, would be able to describe the scattering amplitude as a product of 2 scattering elements with this pole in the middle. This is an exact result in LSZ framework, but I think in S-matrix theory, if you don't want to make connection with axiomatic QFT, you have to make this an assumption. Or maybe, okay, semi-rigorously is the key. Okay, so I'm out of time. This is the question that we will try to answer during the next 2 lectures. So the second lecture will be about causality and what it implies for the analyticity of the S-matrix. Again, without making any assumptions about fields, particles, etc. A third lecture will be about S-matrix unitarity, what it tells us about these elements. And the fourth lecture, we'll try to combine all the knowledge about analyticity and unitarity into discovering our own hadrons. We'll take some experimental data from BES-3 experiment, and we'll try to build some models satisfying S-matrix principles and see if we can extract resonances. Okay, I'll stop here.
All right, thank you, Sebastian. So after each lecture, we have scheduled 15 minutes for Q&A, and also time for further discussions on some concepts. So let me turn it over to the audience. If there's any questions or things you would like to discuss more, yes, please.
In crossing symmetry, why is it different from conservation, like CPT conservation? That's what you mean? I mean, the statement is that the crossing symmetry is a property of analytic continuation of certain S-matrix elements from one to different kinematical region. And as far as I remember, although these proofs are quite complicated, if you want to make this connection, you need to also assume Lorentz symmetry. So, okay, well, you could say that Lorentz symmetry is in some sense equivalent to conservation. But you need CPT and Lorentz symmetry in order to prove crossing symmetry. So maybe that's the statement that I should make. This is the equivalence. Mm-hmm. Yes. I mean, the difference is that, okay, when you, this is a very interesting piece of math, that I didn't want to go into details.
Sebastian, can you repeat the question or comment?
Oh, yes. So the question was that the difference, when we talk about conservation laws, we usually mean continuous conservation laws as being associated with continuous symmetries. but CPT is not a continuous symmetry. So, and first of all, okay, maybe I don't understand fully terminology, but when we talk about parity conservation, this is a discrete transformation, and parity is a conserved object, right? So I would still call it a conservation law, even though we have a discrete symmetry. So the statement that I was making was, if you assume CPT and Lorentz symmetry, you can derive crossing symmetry in the framework of Whiteman axioms, which I didn't define. I don't want to define. I put this name here. You can look them up. And they're very simple, generic assumptions about how Green's functions or correlation functions should behave in field theory. But there's one interesting, non-trivial result in the derivation of this of the crossing symmetry, is that if you assume that Green's function should be invariant under physical Lorentz transformations within Whiteman framework, it implies that they also have to be invariant under complex Lorentz transformations, which is highly non-trivial. And again, this is proved by analytic continuation to sort of complex boosts. So once you have invariance under complex Lorentz transformations, you can rewrite some Lorentz transformations as rotations by imaginary angles, etc. And that allows you to change kinematics of a scattering process in, let's say, physical region for, let's say, pi to pi scattering into a physical kinematics for a process where pion is exchanged with anti-pion. For example, pi plus with pi minus. So this is sort of like a small window into how the proof looks like, but I don't think I either know this well enough or we have time to discuss it in more detail.
Are there any other questions or comments for Sebastian? Yeah.
Okay, let's go.
Hello. So I like physics because it tells us how very complex mechanisms arise from very simple principles. And if this is, this feels like a way to describe something without going to the details and just trying to not violate the laws of physics. But in the end, you don't really know what's going on there in terms of particles, or I don't know, maybe I'm too narrow-minded in this describing the physics thing, but is it a previous step to bootstrap the theory into what reality is, once you have like some parameters that you need to adjust into the experiment, and this is where S-matrix theory comes, or is it deeper than that?
Not sure if I understand the question, but at least I felt in your question some concerns that maybe I can address. So, okay, here was our guiding question, which ends with this loose words without knowing too much. So you said, we want to understand scattering without really describing physics of what's going on in terms of particles and so on. And does it really mean without knowing physics? Like, how do we know that particles are not really strings or unicorns, or maybe some objects for which we don't have classical or even mathematical description yet, right? How do we know that okay, there's good reasons to say that we know that, but let's just fantasize. How do we know that the principle that we can describe certain phenomena by referring to a reduced description in terms of smaller constituents or smaller guiding laws is how the nature really works. And I mean, we know some examples where it doesn't work, like phase transitions in statistical physics. Like phase transitions are collective phenomena. You cannot, and in principle, you can understand, something like boiling water in terms of microscopic interactions between particles in water. But then you realize that it's in the same universality class, so-called, as Ising model, for example, which has completely different microscopic description. So in the question that you asked, there are some already philosophical assumptions about how we should describe physics. Okay, I would say this is as simple as you can go about describing physics. You come up with the simplest possible principles and try to understand how much you can squeeze out of them, right? Without really saying, oh, are hadrons made of unicorns or quarks? Of course, this program will fail eventually because as you will learn, we can squeeze a lot, but not enough. So we will find some constraints for S-matrix elements. We'll see that they will be extremely useful in analyzing things like experimental data or lattice QCD data. But it won't let us make quantitative predictions about things. So you mentioned also the bootstrap. I mean, bootstrap is a word that comes in many different contexts and means many different things. But these two guys, I mean, especially Chu, were leaders of the so-called S-matrix bootstrap program that has also re-emerged recently in like modern theoretical physics. I will mention what that means in a moment. Essentially, Chu's idea was that if you know the spectrum of the theory in so-called ST and U channels, so what kind of resonances appear in different channels, or in the language of S-matrix theory, if you know the singularities of these matrix elements considered as analytic functions, or analytic up to those singularities. Just by using something called dispersion relations, so certain relations that connect imaginary and real parts of these analytic functions, you can essentially reconstruct the scattering matrix for all kinematics and maybe even particles that you haven't seen. Now this, I don't think this program was very successful, and it's essentially based on the idea, on the ideas that are satisfied by a too large class of models that look very differently. Like for example, S-matrix principles, except for this mass gap assumption, should be satisfied by QED and QCD. But of course, QED and QCD have completely different spectrum. These are different theories. Also, the other problem with this program was you don't really have access to enough of the complex energy plane to reconstruct your scattering amplitudes using dispersion relations. And we'll learn this language during lecture 2 and 3. But, so more recently, many people coming mostly from string theory, realize that you can sort of resurrect this S-matrix bootstrap program by taking maybe less ambitious approach. That is, take these principles of S-matrix, apply them to some generic effective field theories that should describe your hadrons, like chiral perturbation theory. So you're already making some microscopic assumptions. And then use these principles to write constraints on the couplings of these theories, or so-called Wilson coefficients. And then you can find some non-trivial constraints on the space of EFTs, and this will guide you in your model building that's based on effective field theories. So this is, I think, a more useful way of looking at this, although, again, the class of effective field theories is so large, and the constraints that you get from S-matrix are not so strong that there still is sort of a lingering possibility of failure of this program. Okay, I talked too much, probably didn't answer your question.
All right, yeah, I know we had one more question, but let me echo a comment. So what I'm hoping that everyone takes from the school, since we have lectures on lattice QCD, effective field theories, and scattering theory, is that these are tools to do physics. Each tool has its use and where it can be applied in a very good manner and where it maybe doesn't work so well. But what I'm hoping is that you take away that if you use these tools in combination, you can get at good physics results. So, you know, let's see if we accomplish that. Did you have a...
Hi, Sebastian. I'd like to thank for the lecture. I have a naive and quickly question. Is there a specific case where the probability conservation can be broken? I imagine something like a non-unitarity, but that occurs in some cases of confinement problem. But I don't know if it makes sense in the scattering picture.
Yes, I mean the most famous example that you know from, you might know from relativistic quantum mechanics or quantum field theory is the so-called Klein paradox. Essentially, the problem is probability conservation can break if you build your theory on a certain Hilbert space, but the interactions that you consider kick you out of this Hilbert space. So you start with some incoming state that lives in your space of considered states, but the interaction is ill-defined. It kicks you out to some larger space. So that means you're losing probability because now it lives outside of your restricted space. And the Klein paradox, or in general what happens in relativistic quantum mechanics, is an example. People try to build a relativistic equivalence of Schrödinger equation. So describe, say, electrons using Dirac equation and some simple wave function. Maybe not simple, it has 4 components, etc., but some kind of wave function object. But if your interaction is too strong, it will allow to produce you particle-antiparticle pairs. And the wave function is something that describes just a single particle. Or it depends on the problem. It can describe many particles, but if you write a Schrödinger equation for a single particle, you just describe single particle. If there is pair, let's say, electron-anti-electron creation, that means that this wave function doesn't describe it. What you need to do is build a Fock space, so extended Hilbert space, which includes sectors for single particle, 2 particle, 3 particle, and so on states. And then each phenomenon that you try to describe will have corresponding wave functions living in these different multi-particle sectors. And this will be the proper sort of description of the system. So that's the first thing that comes to my mind when we talk about breaking of the probability conservation. But there are other examples also related to some ill-defined interactions just in regular quantum mechanics without including relativity.
All right, thank you. Are there any other questions before we go for the coffee break? All right, so we have a coffee break, which is on the mezzanine. I don't know where that is, right over there. We meet back here at 1/4 after. There's a slight change in the schedule. Andre Walker-Loud will be giving the next lecture, and Amy Nicholson is hopefully going to give the afternoon one instead for today. So see you 1/4 after.